All right, class. Back again for one more video lecture. So today is lecture 15 on Scipy root finding. Okay, and if you haven't already, please stop and do a prayer and do the short quiz I prepared for you. Okay? So please pause the video and do that. Alright, great. So today we are going to talk about the root finding tools in Scipy. So this is the first thing we're going to do. Scipy root finding tools. Okay, and then 2, we are going to do, we're going to talk about solving engineering problems a little bit. And I'll say more what that means when we get there. Alright, so that is what we're going to do today. So, just like we did with linear systems, in nonlinear systems, we spent a couple of days learning a little bit of methods. So we learned about how to solve single systems, and the last time we learned about solving multivariate systems. And just as there is in NumPy, linear algebra submodule for solving linear systems in a package called Scipy, there is a submodule for solving nonlinear systems. So the module, I guess I need to write this here. So Scipy root finding. This maybe isn't my best handwriting day. Scipy root finding. Okay, so Scipy, S-C-I-P-Y, stands for Scientific Python. Alright, and the module that we're going to be interested in is called, the submodule is called Optimize. And we will talk more about optimization methods next time, so that will probably, and connect that to nonlinear equations, so maybe that'll help you understand why it's in the Optimize category, or why the name. So to import, we use the command import keyword, import Scipy. Okay, if you want to do the submodule, you would do import Scipy dot optimize, and I usually do that as opt. Okay, opt. So then I can just call opt instead of having to type Scipy dot optimize every time I want to call a function out of there. Alright, so, so let's see. So we'll just skip quick to the chase. So what do we use? The function in Scipy for solving nonlinear equations is called root. So I would call, if I want the solution to some nonlinear equation, which is going to be stored in X solution, some variable, after doing this import, I would say opt dot root, okay, for root finder, and then I would call f, comma, and then the guess, x guess, close dot x. So let me explain what each of these are. Okay, so this is the solution I'm looking for. Okay, that's the function call to Scipy. Okay, f here, this is the function I will define. Function I will define. Okay, and x guess, this is my guess value. Okay, and then this dot will tell me that I want the solution part. So it turns out if I just do root, okay, what it will return, this dictionary, which is a type of Python variable data type that we haven't talked much about, but it's basically a list of things. So it will have something like x, okay, and then it'll have this array with the solution you want in it. But it will also have the error it got to. I can't remember all the right names, okay, and it'll have all these things down here. And if you tell it .x, it will pull out just x as the solution. And so you want to always put this .x at the end. If you're like me, you'll probably forget that it does that, and you'll sometimes forget to put that at the end, and then you'll get your solution and it'll have all this junk. And you go, wait, what did I get? And you got the dictionary. So you need to just go ahead and put a .x on the end there. Don't forget to do that. But you probably will. So when you do, remember to do that. Okay, so I'm going to say a couple things about using root, okay, and then I have an activity worksheet to go through and do. So let me say a couple things first. So maybe let me first say that the reason that we went through learning a little bit about how it worked and learning fixed point methods is because root uses fixed point methods to solve. Some of them are a little more complicated or involved than Newton's method. But when root breaks, and we'll talk about this a little bit in the engineering part, it was important that we understand a little bit how it worked. So it wasn't just for torture's sake that we did that. It was to help us understand how to use root, okay, and how to use it going forward. So that was the first thing I was going to say. Also, Newton's method's pretty fun. It's like the most famous numerical method ever. So we had to kind of learn that one. Okay, so let me just make a couple of comments about this, about what's going to be in this activity to maybe sort of orient you and help you. Alright, so the first one is how you define the function f. Okay, so the function f up here, alright, needs to be defined using def. Okay, it needs to be defined as a function. So an array won't work. So this is a good example. So a good example here would be def f of x colon and then return x squared. Okay, that's a good example. Okay, so here you're giving it the name of the function f. So there's no x part on it. It's just the function name. So it's passing in, that there is a function there. So you can change what's in here and root will know, oh, there's a function here. So what you don't do, okay, bad example would be to just say f is assigned to x squared. Okay, my x was a little wonky there. Okay. So this would just, if I had an array or a value of x, this is just creating a new variable or a new array variable where that stores x squared. That's not what I want to do. Okay, I want to define a whole function. Right, that's the first comment I want to make. The second comment I wanted to make is that the function, holy cow, screwed that up, didn't I? Start over. Just forget I did that part. The function, that looks better. Not a lot, but it looks better. F can be a vector function. Okay, and that's how I can do multiple equations and unknowns. Okay, it's very similar to what we did with Picard's method, and Newton's method, except you don't have to calculate a Jacobian, and you just have to define your function, and you put it in here. So we'll call this root instead of calling that while loop with all the residual mess. We'll just call root, but we still need to define the function. Okay, so let me give a couple examples of good and bad. So good, okay, is going to be def f of x, okay, but remember these are arrays, So I could have x is x0. Well, that's probably the terrible thing. Maybe I don't want x there, do I, to be x of 0? That would overwrite it. I would maybe do, let's see, z here, and then y could be x at 1. And I could make equation 0 to be equal to z times y. I'm just making stuff up now. And equation 1 could be y to the z. Alright? So, and then I would return a numpy array, numpy.array, parentheses, square bracket, equation 0, equation 1. Alright? So that's a good example. Alright? So remember, this is the same thing I had to do last time. So a bad example would be what I told you not to do for the last time. A bad example would be def f of x comma y, okay, and then return, x times y comma y to the x or something, right? So that would be bad example. So now I'm not passing in a vector and I'm returning something that's in this tuple instead of an array, okay? Don't do that. Don't do the bad example. All right. So why don't you take a few minutes and work your way through the activity here. So I'm going to, I'll put a little box here. Do the activity. Oh, holy cow. I just missed. Not so important maybe that I write it nice, but kind of a perfectionist. Activity. Do the box around that guy. All right. It's going to use root. So there are 3 different sections to do with a couple of practice. So you should spend probably at least 10 minutes, maybe 10 to 15 minutes on the activity. The TA should walk around and help you out. And if you have any questions, please ask them. So why don't you go ahead and pause the video, take 10 to 15 minutes and do that. All right, great. So hopefully that activity was useful. I spent a while on that worksheet, or that Python sheet, so hopefully that helped you out. All right, 2. So these are some kind of closing comments that should help you with your homework about solving engineering nonlinear equations, systems or single nonlinear equations. Okay, and really what I want to do is kind of help you with your homework here and help you sort of give you some tips about how to do future problems in your classes. Okay, so hopefully this is helpful to you. Okay, so when we solve nonlinear equations, we have in engineering we have additional issues to work with. Okay, I'm going to highlight 3, but it'll go easier, I think, if I give you an example. So this is an example from my fluids class of an equation we solve, or a set of nonlinear equations we solve sort of to near the end of class. So I'm just going to run them down real quick. So I have delta P over rho G equals minus V squared divided by 2G multiplied by 4LF divided by D. That's one equation. Then I have 1 over the square root of F equals 4 log base 10 of RE times the root of F minus 0.4. And the last one is an equation for RE, which is rho V D over mu. Right? So I'm going to explain what these equations are real quick. So one of the hard parts about this class is if I try and give you some engineering stuff, you haven't learned about it yet. So you don't have to know what this is, but I'll just tell you anyway. So this here, this is pressure loss. So delta P is pressure loss in fluid flowing through a pipe. Rho is the density of the fluid, G is gravitation, V is the velocity of the fluid, L is the length of the pipe, and D is the pipe diameter. And so what's going on here is you have this energy balance, and this is telling you about the pressure loss, okay, and this is telling you about how much friction is going through the pipe, and it's telling you about how much energy you're losing to friction. And this guy down here, F, this is the friction factor, and so this is a relationship basically between how fast the fluid goes and how much friction you have. Okay, so this is a friction factor. This guy here is called the Reynolds number. Reynolds number. Okay, it's dimensionless number, and the Reynolds number then is right down here, and that comes from the density times the velocity times the pipe diameter divided by mu. Okay, so maybe the important thing for our class, so we're going to solve math problems, so I need to tell you what is going to be known and unknown for this given problem. So the knowns would be the density rho, the gravitational constant g, the viscosity of the fluid mu, the velocity of the fluid v, the length of the pipe, and the pressure drop. Okay, so these are known. So we know the speed, and pressure loss. Okay, and the unknowns are going to be the Reynolds number, the pipe diameter, and the friction factor. Okay, so what we're really trying to do here is design a pipe by solving for the diameter. Okay, but in the meantime, we don't know the Reynolds number because I know the velocity and the density and the viscosity, but I don't know D, so I can't know that. If I can't know that, then I can't calculate F. If I can't calculate F, then I can't calculate what D I need, and so they're interrelated. Okay, since they're interrelated, this is a great way to do a nonlinear equation. Okay, so that context, let me talk about the three issues that come up, okay, in solving engineering problems that are different than when we just do these kind of math problems where I just give you straight math stuff. So the first is units. Okay, so we talked about this at the beginning of class, but it sort of rears its ugly head here. You need to be careful with your units. So there are really two approaches that we talked about. So the first is be consistent. Pick a consistent set of units, which are either English or SI. So you pick SI units, newtons, kilograms, and you do that the whole time. The other approach is you can make it dimensionless. We don't really talk about that much in this class. We'll talk about it a lot in fluids if you take fluids with me, about how to make an equation dimensionless. But basically, if you look up here, this Reynolds number, if you look through it, there's no units in this equation. And the friction factor, there's no units here either. This one is in units of height. I know that because I've taught this class a couple times, and I now just know that that's in units of height. You could divide this by height, so if I divided everything by L, okay, then this would have no units either, and that might make this easier to do. Okay, then you could just have equations that don't have any units, just like the math problems we've been doing, so long as you plug everything in and cancel out all their units. Okay, so that's the first thing to worry about, just kind of as a reminder. Number two is maybe the one that's going to trip you up the most on your homework, and that is converting to vector notation. Okay, so basically we're just here converting to standard form, the standard form, and vector notation. So this is residual form f of x equals 0. Okay, it's the exact same form, but it just tends to be a little trickier because now you're looking at things that don't have x's and y's and z's, and you maybe have a harder time seeing it. So I'm just going to do this with this example. So I have three equations here. This one is 0. I'm going to call this one 0, this one equation 1, and this one equation 2. So let me come down and write those in standard form. So in standard form, I'm going to have f0 equals 0, which is delta p over rho g. And then there was a minus sign. Yep, sorry for the scrolling. Just wanted to make sure I didn't make a mistake in my notes. Plus v squared over 2g times 4. Okay, and then I had LF over D, but I'm going to call x0 equal to D over L. Okay, so now I just have an x0 in there instead of D, and then there should have been an L on the top, right? So notice x0 is, my first variable, right? So I don't have all these other things are known. Delta P was known, rho G is known, V, 2G. Okay, these are all just going to be numbers, right? All of these things are going to be numbers, and these are knowns. I'm going to call F my x1. So I'm going to actually erase this guy and make 4x1. I'll have x1 equals F. That was another one of my unknowns. So in my list of unknowns, right, I had D and F. Okay, so I made two of my unknowns in that one. So f0 is some function of x0 and x1, and just a bunch of other numbers. f1 is my next equation, and that is equal to 0, and I just move everything over to the other side. So that's 1 over x1, because I made f equal to x1, minus 4 log 10 times x2 root x1 plus 0.4, and now x2 is equal to my Reynolds number. Alright, great. So now my last one was just f2 equals 0, which was, oh, my notes are falling down over here, pardon me, I'll just fix that, which is now going to be the Reynolds number, which is x2 minus rho v, and then this was d over mu, but I wanted to have, I'm going to multiply top and bottom by L over L, and I want that guy, that is my x0. So that's equal to x2 minus rho v L over mu multiplied by x0. Okay, so now I have in standard form f of x equals, and I just copy this guy from up here down here, delta p over rho g plus v squared over 2g times 4x1 divided by x0. There's the first equation. I have 1 over the square root of x1 minus 4 log 10 of x2 root x1 plus 0.4. It looks like I didn't make my guy down here big enough, so let me get rid of that. And I'll write down here x2 minus rho v L over mu times x0. Okay, so there's f of x equals, and then that's going to be 0, 0, 0. Okay, so I have three equations, three unknowns, x0, x1, x2. Everything here is in terms of knowns, or my three unknowns. So that's how I would write my standard form. And then, now this is all translated. As long as I take care of my units, I have my standard form. I can do a, def of, def of f of x, right? Where I would put in, x0 is x at 0, etc. Okay, and define my equations and do the same thing that I've done before. Okay, that's enough about vector form. Last thing, 3, is getting root to converge. Getting root to converge. Okay, that's the last piece here. So there's two things that it takes to get root to converge. So the first is we need a good guess. So as you saw in the last homework, if you have a system of just 2 equations, 2 unknowns, you can make a plot. And that's a pretty good way of getting a guess. Usually, in engineering systems, you have some physical intuition. Okay? So you can do a plot. Okay? But usually you have, that was going to be a star. It doesn't look like a star to me. Star. Okay? Usually have physical intuition. Okay? So, for instance, you know, the diameter of a pipe, okay, usually is a few inches or less, right? So you might start out and guess, you know, 1 inch. That might be a good guess for a pipe diameter. Or, you know, 1/4 inch, right? Those are pipe sizes you might find at Home Depot. So that's a pretty good guess, okay? If you're doing something physical where, you know, like water's not traveling at the speed of sound or something. For the friction factor, we might guess that it's something like 16 over the Reynolds number. That we'd learn in fluids. That's for laminar flow. That's a pretty simple relationship. So we could, you know, if we guessed a Reynolds number, we could get that out. Or, you know, the friction factor is often like sometimes some number like 10 to the minus 3. So you do a few of these problems and you realize like, well, the friction factor is almost always, you know, small, 0.001, 0.005. So you can guess a number like that. So for your homework, I try and give you direction and give you guesses and stuff to do. So just as you get more experience, you'll start to have some physical intuition. That's usually where you get your guesses from. Okay. The second thing that you might need it to converge is sometimes, even if you give it a good guess, even with a, so I'm going to write this, even with a good guess, okay, it doesn't always converge. Okay, so I'm going to give you a couple things that you can try. So the first thing is that you can try substituting to reduce number of equations and unknowns. So let me show you. So if I look up here, okay, an example of a substitution would be to take the Reynolds number here and to plug it in right there. Okay, it makes it messier, but now instead of having 3 equations and 3 unknowns, I'm down to 2 equations and 2 unknowns, because now I only have is D and F. And if you think about the solver, you know, that means that if it's doing a Jacobian, the Jacobian matrix isn't 3 by 3 anymore, it's 2 by 2. So it has something easier to invert. And so that's one thing. Another thing that you could do, okay, is, you know, get rid of either exponentials or logs, okay. Maybe I'll just write, I'm just going to erase, I put ln there, I'm going to write log, okay. These can be really hard on solvers for various reasons, like you can have a problem if you take a log of a negative number. So sometimes if you've got it, you can take the exponential of it, or you can take the log of it or something, okay? That's just something to try, okay? The last thing is, and this is why I wanted to put this in this lecture, is that you can provide an analytical Jacobian. So it turns out that the root method in the solver, or in root there, it's doing a numerical estimate of a Jacobian. So root uses numerical Jacobian, not a analytical Jacobian, not one where you actually take the partial derivatives. So you can add one, just like you did for Newton's method, and that will help it. Okay, so if you're having a really hard time converging, you can give it an analytical Jacobian. So to do that, right, you would put x, you know, your answer is equal to opt.root, and then you give it your function and your guess. Okay, and then you have another optional argument here called JAC, Jacobian, equals, okay, and then J. And then don't forget the dot X at the end, okay, where J is a Jacobian you define just like in the Newton's method homework we did last time. Define J of X, okay, where this is a vector and this is going to be your matrix, right? And you're going to come down here and you're going to return the NumPy array with, you know, df0, dx0, dot, 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 df0, dx n minus 1, you know, all the way down to the last row, dfn minus 1, dx0, over to dfn minus 1, dxn minus 1, just to remind us what a Jacobian is. Okay? So if you do out all those derivatives and then put those in terms of the x's, all right, and you use this command right there, that argument, that'll provide the Jacobian, all right? And so you obviously don't want to do this every time. You should just start and use it without providing a Jacobian. And if it converges, great. But if you're having problems on your homework in thermo or some other class and it's not converging, then try adding a Jacobian. It can really help the method, especially if you have things like exponentials or logs. And as it turns out, you know, this guy right here, exponentials and logs, in thermo, okay, you won't be able to get rid of them. All right, they'll be there. They're in things like when you're doing liquid-liquid equilibrium problems, there are logs in there, they won't go away, and you're stuck with them. And if you provide a Jacobian, it can help it navigate that problem. Okay? So let me make sure, I think that was all I had on here. Okay, so if you still got some more time, you can go back and finish the activity if you haven't finished it already, or you can start on your homework. Please make sure to ask the TAs any questions you have, and I will be back next time. All right. Thanks, guys.